The paper title of the next paper is One Solution of Memory Communication within Camera Frameworks. This paper has 4 authors. The authors are from Serbia, and the speaker is Mila.
Hello everyone, my name is Mila. I am a PhD student at the Faculty of Technical Sciences, Novi Sad, Serbia, and I will present to you the aforementioned paper that I wrote together with my colleagues Nemanja Lukic, Momcilo Krunic, and Stefan Pijetlovic. So autonomous vehicles, which have the ability to revolutionize the model of mobility in the global world, are equipped with new electrical and mechanical devices for environment perception, communication, and computing. Such systems require the use of multi-core platforms that are able to support complex performance demands. The computer platforms are becoming more and more high performance with concurrent computing capabilities, larger embedded memories, as well as increasing number of integrated peripherals. Following the current technological trends, multi-core and many-core processors are the best candidates for satisfying the functional requirements for infinite performance. Related to the safety issues in autonomous cars, different kinds of sensors are applied, and among all, there is the most often use of different sorts of cameras. However, the simultaneous use of multiple cameras provides a large amount of data, which has an important impact on memory bandwidth. Hence, the importance of the camera in the automotive industry led the authors to present in this paper an example of software architecture of the camera framework in an autonomous vehicle implemented on a multi-core platform. Since 2000, further improvements in single processor design hit major obstacles. The multi-core approach is embraced. Understanding parallel programming and mastering the multi-core challenges became the main goal in almost every part of technological development. One of the articles declared the urgent need to unleash multi-core processor performance in automotive architectures. Software must be parallelized and modified to benefit from new approach to enhanced hardware performance in today's automotive designs. In the automotive industry, there is the need to implement redundant calculations, which can be compared to each other during runtime in order to increase the reliability of the systems and finally deliver products that are state-of-the-art. This need to address that multi-core architecture becomes supported by AutoZA. In one of the updates, AutoZA provided the means to allocate application software components to dedicated cores and facilitate the cross-core communication between those software components via the runtime environment. Dynamic challenges related to the software development in the global scale forced the need that AutoZA consortium introduced AutoSAR Adaptive. In earlier work, co-authors presented one solution of the camera service component based on adaptive AutoSAR, which provides frames from multiple cameras to different client AutoSAR adaptive applications. Also, a novel software framework is developed for efficient streaming applications on single smart cameras, as well as on networks of distributed smart cameras. Distributed smart cameras exemplify two recent trends in visual computing research, and those are distributed processing and embedded computing. Thus, distributed smart camera systems use distributed algorithms to perform complex vision tasks across multiple cameras in real time. Networks of embedded cameras can potentially support more complex and challenging applications than a single camera. Therefore, researchers designed smart camera software architecture for flexibility and reconfigurability, which consists of several layers grouped into two frameworks. First one is the digital signal processors framework running on every DSP in the system, and the smart cam framework running on the network processors. This paper represents one of the possible designs of the camera framework, suggesting the use of the C++ programming language. The camera framework is used for exchanging information between producers and consumers so that each software component has access to the frames it needs, regardless of its location. There are several cameras of various resolution connected to the camera framework producer. The camera framework services producer software components and consumer software components. The camera framework does not abstract the runtime environment, but simply provides a mechanism by which the real-time environment can transfer camera data in addition to the normal vehicle data. Thus, this provides a unified data path for both video and vehicle data. Here you can see the proposed architecture. At initialization, the underlying framework returns an OPEC handle. The camera framework would allocate a set of contiguous buffers in memory, which are transparently managed by it. As the camera framework needs to support several sets of cameras, each with different resolution, frame rates, and consumers, a pipeline handle is returned, indicating which camera set is being defined. The construction of the camera frame distribution is implicit in the real-time environment software component definition. So software component A defines it received data via a real-time environment message from software component B. The same video data is also sent to a real-time environment to software component C. Thus, from a component perspective, we need a way to associate and disassociate a buffer to end software components. Internally, there is a management structure which manages a list of consumers for each buffer entry defined. When the list is empty, the buffer can be reused. There should be enough buffers allocated such that acquire buffer function is always able to find an available buffer. The real-time environment network passes a buffer ID, which to it is an OPEC structure the size of an integer. The buffer ID can be passed to another function to enable access to image data stored from that buffer ID. This allows direct access to the buffer raw data, but does not cause a large memory copy via real-time environment. As shown in the figure, shared memory component is used to allocate and manage blocks of memory, which are visible across processes. Each connected camera sets results in a pool of images being created by the camera framework. The principle limits contention to users of a given pool rather than to all users of the memory allocated. So for example, the driver monitoring sees only the driver monitoring pool, but not the front camera pool. Each user, producer, and consumer has the shared memory area mapped into its address space. Only the producer can write images to the pool, so consumers can share the same image without corrupting each other's data. The producer must explicitly state at what point the buffer is now complete and can be provided to the consumers. At this point, the buffer page must be set to read only to detect and prevent any further writes to this data. The produce the next frame, the producer must ask for another buffer and write to this, and then push this one to the consumers. One of the main problems that arises in the modern automotive industry is the need to collect enough data and compare results of different actions during driving, but at the same time maintain safety. In order to overcome this problem, shadowing technique is adopted. In shadow mode, the car isn't taking any action, but it records when and what action the autopilot would take. By comparing the results, autopilot errors can be eliminated without risk, and confirmed solutions and collected data can be used for further development. Communication between the primary partition and the shadowed partition is a case of remote host communication. In this case, the remote manager is responsible to serialize image to an external bus so image can be sent over the Ethernet transport stream and reserialized by the receiver at the other end. Camera framework opens one base address register per exported pool, which allows host A to map memory area to host B. Only the pools which are explicitly shared are sent to shadowed system, and as write happens directly to the destination memory area on shadow, no copy is needed. Camera framework uses interrupts to avoid the shadowing having to pool to know when new data arrives. In order to test performances of the implemented solution, we have considered the following two components. First one is the producer, which reads from a video file, decodes the video file with OpenCV, writes the current frame to a specific location given by the memory manager library, and publishes real-time environment messages to the consumers who need the images. The second component is the consumer that subscribes to the real-time environment messages from the producer, which contains a memory address for the frame sent, so the consumer can use the same memory manager library to access the image. The producer runnable is responsible for calling the step function of a producer. The step function consists of fetching the next frame from the video file, decoding it with OpenCV, writing the decoded image to memory, and distributing the real-time environment messages. What is measured is the time that the process takes every time it's waken up by the scheduler, which in this case translates directly to the time of the step function. To visualize how long the process takes, we use the LTTNG tool. LTTNG traces showed that the first steps of producers takes more time than the others. After profiling and tracking the steps, it was found that it's a peculiarity of OpenCV video capturing that retrieving the first frames always takes more time. As an experiment, capturing the first few frames is moved to initialization, but this has caused the consumer not to get the first few images. Here, the figures show the time from the beginning of retrieving the next frame to the end in milliseconds, when the second and third producer are on the same core and the first producer is on the second core. So in this paper, we have described the transition from single core to multi-core systems and the important benefits that have come with this adjustment. This change has conditioned many new trends in the automotive industry, as well as the adaptation of software to take full advantage of new modern platforms. Since autonomous or highly automated driving requires that vehicle must be aware of its surroundings, environmental model is built to use sensor fusion approach, including multiple cameras. Here we have shown one possible solution for the implementation of the camera framework for today's multi-core platforms relying on shared memory and shadowing approach. In further development, the implementation can be improved by using PCI instead of Ethernet, whose higher bandwidth will support faster frame copying and more efficient communication between remote hosts. So that was all, and thank you for your attention.
Okay. Okay, thank you. Thank you very much for the speaker's excellent and attractive presentation. So, any comment or suggestion from audience? Any comment or any suggestion from audience? Oh, okay. I have a simple question. So, in your study, so you find the one solution of memory communication with a sharing buffer. Okay. So, besides the solution of memory communication, what is the maximum data rate required when the multiple camera framework is used in the system?
I'm not sure. Yeah, I can check with my colleagues who did those measurements and then get back to you if you're interested. Yeah, I don't have that information right now.
Okay, thank you. Thank you very much. Okay. So any other question from audience? Any other comment or question from audience? Okay.